In 1805, a French mathematician named Adrien-Marie Legendre published a surprisingly simple idea. If you have a cloud of noisy observations, find the line that makes the total error as small as possible. Nudge the line, measure what's left over, keep the version that's less wrong. Next to ChatGPT, that sounds laughably primitive, calc, but it is still the basic idea behind how we train modern AI. Start with the simplest machine that can learn anything at all. Feed it inputs, it makes a prediction. Compare that prediction with the correct answer. If it's wrong, nudge the parameters. Then do it again, a few million times. Predict, measure error, adjust, repeat. That is the entire loop. But a line can only ever cut the world in two, and the real world isn't shaped like that. No matter how you rotate it, no matter where you slide it, some points end up on the wrong side. So, researchers started asking a much better question. What if the machine could learn the rules itself? In 1958, Frank Rosenblatt built the perceptron. Inputs arrive, and each one is multiplied by a weight. Add them up and fire if the total clears a threshold. Show it examples. Let it be wrong. Nudge the weights. Try again. Nobody wrote the rules, they supplied the examples. Then came exclusive, or 4 cases and a single perceptron could not learn them because no straight line separates them. The idea was right. The machines were not yet ready. One neuron isn't enough, so stack them. The first layer learns crude patterns. The next combines those into better ones, and so on. Nobody specifies what each layer should look for. It falls out of the training. Raw pixels become edges, edges become shapes, shapes become a face. But how do you train all of those layers at once? Back propagation. Run the error backwards through the network, working out how much each parameter contributed to it and adjust millions of them at a time. In theory, straightforward. In practice, brutal. Gradients vanished, or they exploded. Computers were too slow and there was not enough data. Then 3 things showed up at roughly the same time. Enormous datasets, hardware that could do the matrix maths absurdly fast, and architectures that actually trained. The learning loop didn't change. Everything feeding it did. In 2012, AlexNet cut the ImageNet error rate by a third in a single year. Not an improvement on the trend, a break in it. Within 3 years, machines were beating people at the same task. The lesson was blunt. More data, more compute, better architecture, and it gets dramatically better. Which raised an obvious question. If they could learn images, could they learn language? Language is hard because words depend on other words. The dog chased the ball because it was tired. What does it refer to? The dog or the ball? You know the answer is the dog because balls don't get tired. But notice where that evidence sits. 3 words after the pronoun. The early language models were recurrent. They read one token at a time, carrying a memory forward, which is slow and cannot be parallelized. Then, in 2017, came the transformer and its key idea, attention. Instead of marching through the sequence one step at a time, every token looks directly at every other token and weighs which ones matter. It attends most strongly to dog. And unlike a recurrent network, this parallelizes, you could simply make it bigger. So people did. And something strange started happening. The training objective is almost embarrassingly simple. Show it some text with the end cut off and ask it to guess what comes next. The capital of France is, and it puts almost all of its probability on Paris. Score the guess, adjust the parameters, repeat a few trillion times. Predict the next token. That is the entire objective. But past a certain size, these models stopped merely finishing sentences. Translation, summarization, arithmetic, writing code, chains of reasoning, conversation. None of it trained for directly. A staggeringly narrow goal produced staggeringly general abilities. So when you look at ChatGPT, it is tempting to think you're seeing something entirely new. But zoom out. 217 years and the loop underneath has barely moved. Make a prediction, measure the error, change the parameters, try again. What changed was the scale it was pointed at. The revolution wasn't one magical algorithm. Ya ondakuon, it was finding out how far a very simple idea would go.